Hello everyone, I am Saifeng. I'm very glad to have this opportunity to introduce to you our study recently published on JMRI, Stability Weighted Imaging and Quantitative Stability Mapping of the Cerebral Vasculature using Ferumoxytol. The purpose of this study is to demonstrate the potential of imaging both cerebral arteries and veins with Ferumoxytol using SWI and QSM. First, we performed phantom studies to determine the relationship between the apparent stabilities and the concentration of Ferumoxytol at a given field strength. Next, we used the simulations to study the size of the smallest vessel that can be seen with a certain concentration of Ferumoxytol. Finally, we demonstrate the feasibility of this method using in vivo data. The results showed that the contrast to noise ratio for cerebral vessels can be enhanced with Ferumoxytol and SWI. The apparent stabilities of the arteries with Ferumoxytol can be reliably quantified using QSM. The cerebral vascular abnormalities are found to be the source of many neurologic diseases. Hence, it is very important to image the cerebral vascular abnormalities. This can be done by using the conventional MRI angiography. However, imaging the vascular abnormalities at the micro level is still very challenging because of the limited contrast to noise ratio at a high imaging resolution. For imaging the venous abnormalities, this problem can be partly solved by using the SWI technique. As shown in this example, SWI can significantly improve the visualization of deep medullary veins and venues, and this level of visualization is very similar to the left image, obtained in a postmortem study. Although SWI is a powerful technique, it is primarily used for imaging the veins, not the arteries. Why is that? And how can we use SWI to improve the visualization of small arteries? Let's take a look at how SWI data are generated. In SWI, the magnitude and phase information is combined by creating a susceptibility weighting mask from the phase images, and then multiply this mask into the magnitude images. The phase is proportional to the field variation, and the field variation is a function of susceptibility difference. For veins, the susceptibility difference is close to 0.45 ppm due to the deoxyhemoglobin in the venous blood. This is why there is rich information of the veins in the phase images. By combining phase with magnitude images, the contrast of the veins can be improved. For the arteries, however, the susceptibility difference is close to zero with respect to the surrounding tissue. Consequently, to use SWI to image the arteries, we need to find a way to modify the susceptibility of the arterial blood, and this can be done by using Ferumoxytol. Ferumoxytol is a type of ultra-small superparamagnetic iron oxide. It is an FDA-approved iron-based agent for treating anemia, but it has also been used as an off-label contrast agent using its T1 shortening effect. In this study, we are mainly using the susceptibility effect of Ferumoxytol. First, we performed phantom studies and determined the relationship between the apparent stabilities and the concentration of Ferumoxytol at 1.5T, 30, and 70. At each field strength, the apparent stability increased linearly as the concentration increased. The product of the apparent stability and the field strength is constant at different concentrations due to the magnetization saturation. Using these relationships, we can predict the apparent stability for a certain dose of Ferumoxytol. For example, with a dose of around 2.5 mg per kilogram at 70, the apparent stability of the arterial blood will be close to that of normal venous blood, and this dose is much smaller at 30, close to around 1 mg per kilogram. But what is the size of the smallest vessel that is visible at a certain dose, say 2.5 mg per kilogram? To answer this question, we performed simulations based on these relationships just determined in phantom studies. Specifically, we simulated veins with diameter less than 1 pixel and measured CNRs of the veins on different types of images. We found that with higher concentration of Ferumoxytol, smaller vessels can be determined, but the size of the smallest visible vessel is dependent on the imaging parameters and the post-processing techniques. Higher imaging resolution and longer echo time leads to a better detection of small vessels. Among all the image types, we observed that TSWI was one of the best images to be used for detecting small vessels at different ferumoxytol doses. Specifically, at echo time of 10 milliseconds, a voxel aspect ratio of 1/8 with 4 mg per kilogram ferumoxytol, arteries with diameter approximately 50 micron can be detected using TSWI. We further demonstrated the feasibility of this method using in vivo data. This is an example of visualizing arteries and veins in the basal ganglia. This figure shows two arterioles in the right putamen and right thalamus, as indicated by the red arrows. These can hardly be seen in either the pre-contrast or the post-1 mg per kilogram ferumoxytol data. Here is another example of visualizing cerebral arteries and veins. Again, tiny vessels were not visible in the pre-contrast or the post-1 mg per kilogram data, but became visible in the post-3 mg per kilogram data. These vessels are very likely cerebral arteries. Because of the naturally higher stability of the veins than the arteries, the visualization of the cerebral veins was even better than the arteries. In this final example, we demonstrate the visualization of tiny branches of the arteries, which were not visible in the pre-contrast MRI. The visualization of these tiny arteries agrees well with the one on the right from Salomon's Neurovasculature Atlas. To separate arteries from veins, we can use both pre- and post-contrast data. The veins are bright on the pre-contrast QSM, but dark on the pre-contrast SWI, while the arteries are bright in the pre-contrast magnitude image. Then, using the connectivity of the pixels, we can try to separate arteries from veins. Finally, we measured the apparent susceptibilities of the anterior cerebral artery and the internal cerebral vein. We found that the measured susceptibilities of the arteries agreed well with the predicted values using the relationship we determined in the phantom studies. But the measured susceptibilities of the veins were underestimated. This could be due to the phase aliasing and the increased effective vessel diameter. In conclusion, we demonstrated the feasibility of ultra-high resolution MRAV using USPIO enhanced SWI and QSM at 70. We studied the impacts of ferumoxytol dose, imaging parameters, and post-processing techniques on the CNRs of cerebral vessels. This method can be a powerful tool in detecting microvascular abnormalities which may not be visible on conventional MRI. I would like to acknowledge the ground supports and thank you for your attention.